Hey everybody, welcome back to chemistry. And so now we are at a point in chapter 2 where we're going to try to understand some details of something called electronic structure of an atom. So here what we're trying to understand is if you look at an atom and it has a lot of electrons, where can these electrons be found around the atom? And so at this point you know that they're going to be outside the nucleus, but we want to know in a little bit more detail exactly how far away they are going to be from the nucleus of the atom. And so I want to point out this is kind of important because if you understand the electronic structure of the atom, it tells you something very important. And so it will explain to you why is it when you're looking at the periodic table that elements in the same column have similar properties. And again, that can be explained by understanding something about the electronic structure of the atom. So let me just kind of give you a quick example of that idea. So here we have a periodic table. And then, as I kind of pointed out to you before, we can sort of examine the first column of the periodic table. And if you see those elements there in that red rectangle, it begins with lithium, and then sodium, potassium, rubidium, cesium, and francium. All those elements are part of the group called alkali metals. And as it turns out, those 6 elements have very similar properties. Those properties tend to be different than the properties of the other elements in the periodic table. So for example, all of these metals are very shiny. They all have about the same amount of electrical conductivity. They all have relatively low melting points for solids. And also remarkably, all these metals react violently with water. So if you put these elements into water, you would get an explosion. And actually you can see videos on that of YouTube. Just Google onto YouTube sodium and water and you can see people dropping neutral sodium metal into water and the water explodes. And it's because the sodium metal is reacting violently with the water. And so all the alkali metals tend to do that. And so there's a particular reason for that, and the reason is because they all have a similar property in the structure of electrons around their atoms, which is different than the electron structure that is found in the other atoms of the periodic table. And we'll learn about that maybe about 3 or 4 presentations from now. And so another example of this is the last column of elements is the noble gases. And so these elements in this group are helium, neon, argon, krypton, xenon, radon, and I forget what Og is, but don't worry about that because you don't have to know that one. These elements also have similar properties which are different than the properties of the other elements in the periodic table. And so what's remarkable about the noble gases is if you find them at room temperature and pressure, what you'll see is that the individual particles are comprised of just single individual atoms that are kind of well separated from each other in the gaseous state. That's kind of rare in the periodic table. Most of the time when you have an element, it's stuck on to another one of itself or to a different element in the periodic table. With the noble gases, the particles are just single atoms in space by themselves, and they tend to be very unreactive. They don't want to combine with other elements in the periodic table. And so the reason why these elements in the noble gases have this similar property is due to a similarity in their electronic structure, which is different than the electronic structure of the other atoms in the periodic table. So to understand this, we need to know something about the electronic structure of an atom. And so what we're going to do is we're going to talk about it sort of in a fundamental level, and then we're going to increase the complexity as we go on. And so one question you might want to ask yourself is, let's say you're looking at an individual element like carbon. And so you know that carbon has an atomic number of 6. It has therefore 6 protons. If it's a neutral atom, it'll have 6 electrons. You might wonder if the 6 electrons in carbon are all exactly the same distance away from the nucleus, or are they varying distances away from the nucleus? And the latter answer is correct. And the places where those electrons in carbon go, certain distances away from the nucleus, are called shells. Also, you can call these places where these electrons go, or you can call them energy levels. And so I have sort of a picture of that here, but let me just kind of draw this a little bit here. So let's say you're looking at a carbon atom. And so it has 6 electrons. But you also know that in the nucleus of carbon, it has an atomic number of 6. So it tells you it has 6 protons, and also there are going to be about 6 or 7 neutrons in the nucleus as well. So what I'm going to do is I'm going to represent the nucleus of carbon as here a little ball with a plus sign. Where are the electrons? Well, you know that the electrons are outside of the nucleus. So let's talk about where they're found. And so what you'll find is that of the 6, the first 2 electrons are some distance away. And this first distance where you can find the first electrons on carbon is called the first energy level. I'm just going to write E for short for energy. So this is the first energy level. And so we can find 2 electrons, say, out here. So I'm representing those as dots. Now, what I've drawn is kind of a misrepresentation of what the electrons look like and what they're doing in the atom. So what I've drawn is it almost seems like electrons here are traveling in an orbit around the nucleus. And if you were to say Google carbon, you'll get this nice picture of the nucleus of carbon. You'll see these electrons orbiting around the nucleus. One of the things you would learn if you take more chemistry is, in fact, the electrons do not travel in trajectories in an orbit around the nucleus, say like planets around the sun. Instead, their motion is very unusual. We're not going to talk about it in this class, but if you're interested in more chemistry, you'll learn a little bit more about the motion of electrons. Another thing is this kind of implies that, again, the electrons are sort of in a 2-dimensional orbit, but what you have to remember here is that here, this really isn't a orbit. Where the electrons are found in one or more something called orbitals. And so what I've tried to do is I've tried to redraw this to maybe look more like a 3-dimensional sphere. So in this first energy level, it really isn't an orbit so much. It's more of a kind of a ball or a sphere around the nucleus where you can find the 2 electrons. And then what you have now with carbon is you have 4 more electrons. So where do they go? One of the things you'll have to learn is that once you have 2 electrons in the first energy level, the first energy level of carbon is filled. So the next 4 electrons go into a higher energy level that's further out. And so here we have a second energy level. And again, this is not so much an orbit, it's a certain distance away from the nucleus, but it's kind of a 3-dimensional sphere. And so here you'll find maybe 4 more electrons of carbon. Now here's the thing. We have 4 electrons here in this second energy level. Let me label this. This is the second energy level. But one of the things we know from experimentation is that the second energy level can have, in fact, a total of 8 electrons. So here, the second energy level, you can think of it this way, is that of the 8 slots that you can put electrons into, 4 are occupied and 4 are unoccupied. Now, there's actually even greater energy levels than that in carbon. There's a 3rd energy level, which is an even larger sphere, and a 4th energy level, which is even a larger sphere. And so one of the things you'll have to learn is that the 3rd energy level can accept up to 18 electrons, and the 4th energy level can accept up to 32 electrons. But because carbon only has 6 electrons, the first 2 fill up the first energy level, the next 4 go into the second energy level, there are 4 more slots left, and the 3rd and 4th energy levels are empty. So this is sort of a nice picture, a simplified picture of carbon. One of the things, again, I probably should repeat, is each of these places that are getting further away from the nucleus, where you can find electrons in the atom, they're either called a shell or an energy level. Okay, and so here in this slide, I'm just kind of mentioning that you have to remember that the first energy level with its small volume can only accept up to 2 electrons. The second energy level can accept more electrons because it's a larger volume. This can accept up to 8 electrons. And the third energy level, even a larger volume, it can accept up to 18 electrons. And then the fourth energy level can accept up to 32 electrons. And so you might be wondering, do I have to memorize these numbers? And actually, you're not really. What you can do is just remember this. If n is the number of the energy level, whether it be first energy level, n would be 1, the second energy level, n is equal to 2, 3, and 4, to figure out the total number of electrons in that energy level, you take the energy level number and you square that, and you multiply by 2, and then this number tells you the total number of electrons in that energy level. And so let's do that calculation really quick for the fourth energy level. And so if you were in the fourth energy level here, how many total electrons could be found here? Okay, so it'd be 4 squared, which is going to be what? That's going to be 16 times 2 is going to be 32. So you can find up to 32 electrons in the fourth energy level. Now, will you find that number of electrons in the fourth energy level? Well, it depends on the atom. So for example, with carbon, we only had 6 electrons, right? And they tend to go into the innermost energy levels first. And then once those are filled, then they go into high energy levels. So with carbon, the fourth energy level has 32 slots for electrons, but it's empty. I think you can see that you're going to need larger atoms with more electrons. You need an atom with 29 electrons or more before you start putting electrons in the fourth energy level. And so we'll talk a little bit more about that later. Okay, so we move on here. Okay, so now let's go ahead and do some problems. And so here's our first practice problem. It says, a neutral oxygen atom has 8 electrons. How many electrons are found in the first, second, and third energy levels? And if I can reduce the slide. Okay. So there are a number of ways we can solve the problem, but what we might want to do is first sort of recount how many total electrons can be found in each of these energy levels. And so I'm hoping you can go ahead and figure out that for the first energy level, how many total electrons would be found? It would be 1 squared, right, times 2, which is going to be a total of 2 electrons. And the second energy level is going to be 2 squared times 2, which is a total of 8 electrons. And then in the third energy level, it's going to be 3 squared times 2. 3 squared is 9. 9 times 2 is 18 electrons. Now, I think you can sort of figure out how many of oxygen's electrons are going to be in oxygen's first energy level, second, and third. Oxygen only has 8 electrons. So the first 2 will go into the first energy level. So oxygen has 8 electrons. 2 have gone into the first energy level. What's left? We have 6 electrons left. They will go into the second energy level. And so you can see that the second energy level can accept up to 8 electrons. And so the second energy level with oxygen is not full. And so that means that in the second energy level, 6 electrons are there. And then there are 2 spots that are empty. And therefore, since we dealt with all of oxygen's electrons, there are going to be no electrons in oxygen's third energy level. Okay? So we will write the answer here. So oxygen's first energy level has 2 electrons. The second energy level has 6 electrons. And the third energy level has no electrons. Okay, so let's go ahead and do the next question. Let me erase this. Okay, the next question reads as follows. It says, how many electrons are found in the first, second, third, and fourth energy levels of a neutral chlorine atom? Okay, so the only way you can answer this question is you know how many electrons can be found in a neutral chlorine atom. And so the periodic table will have to be used to give you that information. So the first thing you have to remind yourself is that the symbol for chlorine is Cl. And so you go to your periodic table here, and then you see where chlorine is in the periodic table. And so here, what I see chlorine here is located here in the periodic table is atomic number 17. And so that gives us some information about chlorine. If it's atomic number 17, that tells you that chlorine has 17 protons and 17 positive charges. The chlorine atoms in their nucleus also have some neutrons, but that's not really important in this problem. We know that this is a neutral chlorine atom. So therefore, if it has 17 protons and 17 positive charges, it must have as many negative charges as positive charges. So if it has 17 positive charges, neutral chlorine would have 17 negative charges. And so it's going to have 17 electrons. So now we know that chlorine has 17 electrons. And so let's figure out, again, how many electrons are found in each of these energy levels of chlorine. So I'm going to go a little bit faster here. So you might remember that the first energy level of any atom can have up to 2 electrons. And so of chlorine's 17 electrons, the first 2 are going to go into the first energy level. So the first energy level has 2 electrons. The second energy level, you may remember that the second energy level can have up to 8 electrons. And so chlorine, we started out with 17 electrons, we reduced it by 2, we're now down to 15. Of those 15, 8 will go into the second energy level. Now the third energy level, how many electrons can be found there? Well, the third energy level can have up to 18 electrons. So let's figure out how many electrons do we have left in chlorine after we put 2 in the first energy level and 8 in the second. Well, chlorine has a total of 17 electrons. 10 of them have gone into the first and second energy level. So what we have is 7 left. And so 7 here will go in the third energy level. Now remember, the third energy level can accept up to 18 electrons. So you could put a lot more in here if you wanted to. So that pretty much does all of chlorine's electrons. And so you can imagine that the fourth energy level of chlorine doesn't have any electrons at all. So that's 0. Okay, so we move on. Next slide. So if I can increase the slide just for a second, please. So I want to point out a very important point here which you need to understand. And this is, I think, for me, when I was learning general chemistry, this was a difficult, subtle point for me to understand. But the point is this: an electron gets more energy the further away it gets from the nucleus of the atom. And so I have an explanation there on that slide, and I'm hoping you'll read about it. But let me go ahead and reduce the slide and sort of give you sort of my 10-cent reason as to why is it as electrons get further away from the nucleus are they said to have more energy. So as you know, all things have energy. And so I'm going to give you sort of a simplified analogy to help us think about this. So imagine I have a brick in my hand. So I think you know that this brick has some energy to it. You'll learn more maybe later on if you take more chemistry, the kinds of energy it has. But I think one thing you know is if I hold the brick close to the ground and then underneath that brick I have a glass test tube, if I drop the brick, which is close to the ground, right on top of the glass test tube, that brick will maybe shatter the test tube into pieces. And so that tells you that the brick must have had some energy to shatter the test tube. Now I think you also know that if I drop the brick from further up on the test tube, then it's going to shatter the test tube even into smaller pieces because the brick further up had even more energy. So what that tells you is that due to position, a object like a brick can have more and more energy. And so not only does this apply to things like bricks, but it also applies to things like charges. And so let's say you have a positive charge here, and let's say you have a negative charge here. So you can think of this single positive charge, if you want, as a proton. And you can think of this single negative charge as an electron. And so if you have these charges pretty close, what they're going to do is they're going to want to be attracted to one another, and what they're going to do eventually is they're going to stick to one another like that. And so when they do that, they are lessening their energy, and now this is a very stable complex. And so to go from charges that are kind of far away to charges that are really close together, there's not much of an energy change here. Here, the charges here are pretty close. They have relatively low energy. When they stick together, they even have lower energy. Now imagine if you have charges that are much further away. So we have a positive charge way out here, and we have a negative charge way out here. Well, they will be brought together with the force, and then the charges will stick together. And then what will happen is way out here, these charges have far more energy than if they were close together. And so if you did bring them in, they're going to release all that energy, sort of like having a brick far off, and when you drop it, it releases a lot of energy. So the point I'm trying to make is this: when the charges are further apart, then the energy of the charges is going to be greater. So what this means practically is the following. So if you have a nucleus here, and you have an electron that is out here in the first energy level, it has a certain amount of energy. Now, if the electron is out here in the second energy level, it's going to be further away from the positive charged nucleus, and so it's going to even have more energy. And if you have an electron in the third energy level, it's even further out, and so it's going to even be more energy. Now, one question that is often asked is, well, why isn't it that this electron just can't fall into the nucleus? And that is a wonderful question to ask. And this is what scientists in the early part of the 20th century were asking themselves as well. Why are these electrons not falling into the nucleus? And so here, what we've learned about atoms is that they don't follow the regular rules of classical mechanics. You would expect electrons to at least spiral into the nucleus, but they don't. Here, these electrons manage to stay in stable positions away from the nucleus. And so this is not predicted by classical mechanics. You would learn, if you take another chemistry class, why is it that electrons are stable around the nucleus? And here it's because electrons don't follow classic mechanics, they follow something called quantum mechanics. And quantum mechanics predicts that electrons will be stable at a certain distance away from the nucleus. But the important point here is that as an electron gets further and further away from the nucleus, the more energy it will have. So thank you for listening to that presentation. We'll see you next time.